Okay, so we are talking about a language accepted by a DFA, that string accepted by the DFA. So, this was the example we have taken in the last class. So, suppose we have this DFA which is having these states q 0, q 1, q 2, q 3, q 4, and the q 2 is the final state and q 0 is the starting state, and we have this rule. And then we have seen this language is, this DFA is accepting some string, like this example we have taken w, say 0 1 1 1 0 1. So, we want to define the delta hat. We start with the q and on this w. So, how we do that? So, this is by definition of the delta hat recursively, I mean the induction, I mean way. So, this is nothing but delta hat of. So, this we write in x a. So, delta hat of q 0 x, then we see a 1. So, this is also delta hat of this. So, x is also can be written as this. So, so this is delta hat of q 0, no delta of, so delta hat of q 0 comma. Now, this is our x. So, 0 1 1 and then we have 1, sorry, this one is 0 and then we have 1. So, this way if we continue, so this is again delta of, then this delta hat again we can define as delta of delta hat of q 0 0 1 0 1 comma 1, then comma 0, then comma 1. So, this we can define as delta of. Now, this delta hat, now we have only 2. So, this we can just define on delta hat of q 0 x. This is the delta hat of q 0, sorry, this is delta hat, but delta hat is on one symbol is basically delta of 0, actually delta hat, then delta hat of q comma epsilon. So, this is say only one symbol a. So, this we can write delta hat of q comma epsilon is epsilon. So, this is nothing but delta of q comma a. So, once it is reached to a single symbol, it is this. So, this is delta of q comma q 0 comma 0, then comma 1, then comma 1, then comma 0, then comma 1. So, if you do that, so now what is the q 0 comma 0? Q 0 comma will go here, then 1 will go here, then 1 will go here, then again 1 will come back here, then again 0 will go there, again 1 will come back here. So, that means this delta hat of q 0 comma this w is nothing but q 2, which is the accepted state. So, this is a string which is accepting. So, this is just an example. So, now we define the language of a deterministic finite automata. So, such a string which is reaching us to the accepted state, such a string if we put it into a set bag, that bag is called language, and that language is called the language of the DFA. So, delta hat of q 0 comma w, if it is belongs to f final state. So, then we say w is accepted by the DFA. Okay. So, this is the set, such set is called the language of a DFA. So, if we so this is the set of all string such that delta hat of q 0 w is belongs to f, then this is called language of the DFA. So, if our string, so this is consists of all possible such string which is accepting, which is reaching to us the accepted state. We start with the starting state, we keep on reading the input symbol and then we keep on changing the state depending on the input, and then finally, if we can reach to a final state, then that string is accepted. Now, this language is the collection of such accepted string is called the language of the DFA, and this is defined as. So, if our DFA is A, this is consist of 5 tuple q sigma delta q 0 f, this is the f, then this is called L of A, language accepted by this DFA. Okay. This is the set of all string w that start with the starting state, and if it is end with the final state, then it is called the language, the set of all such string, then the string is accepted by the DFA, and the set of all such string is called the language. If we put into the bag, that bag is the language of the DFA. Okay. Now, we define what do we mean by a regular language. So, this is the input alphabet or alphabet symbol, input symbols, and we know the language. So, language is any language is a subset of sigma star. It is a collection of string, any collection of string is called a language, including the null string. Okay. Then when we say this is a regular language, if it is a language of a DFA, if there is a DFA which is accepting all the string of it, then we call this a regular language. So, is a regular language if this L is L of A, where A is a DFA. So, that means, if the all string, if there exists a DFA which is accepting the all the string of this language of the string of this set, then we called this language is a regular language. So, any such collection of the string which is accepted by a DFA is called a regular language. We will take some example of some language and we will determine whether this is a regular or not. To be a regular, we need a finite automata which is accepting that all member of that set. Okay. So, we will take some example. Okay. Regular language means a language will be regular if there is a DFA, deterministic finite automata, such that which is accepting this language, such that if we take any string from this, for all string from this, and if this is say q 0 f, delta hat of q 0 w will be f for all this. Then we know this is called language of that DFA. Then we say this is a regular language. If a DFA exists, if a finite automata exists, then we say this is a regular language. Okay. So, we will take some language and we will determine whether it is a regular or not. That means, we have to find out whether there is a automata which can accept that. Okay, let us take some language, some set of string. Okay, here our input symbol are binary 0 or 1. Now, let us define some language W, which is W is a string with odd number of ones. W is a binary string, all binary string, collection of all binary string with odd number of ones. Odd number of ones. That means, we have given the string is coming from the input symbol 0 1. So, it is a sequence of 0 1 bits, 0 1 symbols. Now, we consider the all such string which is having odd number of 0, like this is a string, this is only 1 1. So, this is a one string 1 0 1 1. This is another string. These are all string which is having odd number of ones, 1 1 1 1 1, 5 ones, 1 0 1 1 1 1, 5 ones. So, any such possible. So, this is a collection of all such string. So, this is our language and we want to check whether this is a regular language or not. So, for that what we need to do? We need to have to be a regular, we need to have a DFA which is accepting this, whose language is the same as this language. So, we need to have a DFA which is accepting all the string where the number of ones is odd. So, let us try to. So, the question is this regular? Regular. So, for this we need to be regular, we need to have a DFA delta Q0f such that the language of the DFA should be same as this. That we have to check. So, let us try to find a DFA. Yeah, so this okay. So, let us start with Q0, this is the starting state, and we have a Q1. Suppose from here, if we take a input 1, we are going here, if we take input 0, and from Q1, if we take 0, will be remain at this, and if we take a 1, we have to come back here. Okay, very simple DFA. So, what is the DFA? So, this is our DFA A, which is consists of 5 tuple Q sigma delta Q0 F. Now, what is Q? Q is basically only 2 state we have, Q0 Q1 and sigma is 0 1. We have binary input 0 1. And Q0 is this one, QF is F is Q1 final state, we have only one final state, and delta. Delta consists of, delta is the rule. So, this is we have 2 state Q0 and Q1. So, if we had Q0, this rule is telling if we put a 0 input, so delta of Q0 of 0, it is Q0, because this is Q0, and delta of Q0 of 1. If we had Q0 state, if you read a 1, then we will go to Q1, that is the rule Q1. Okay. Now, from Q0 delta of Q1, if we put a 0 input, will be remain at Q1, and from Q1 if we see a 1, we will come back to the Q0, that is the rule. So, this is a finite automata. Now, we have to check what are type of language this automata is accepting. Okay. So, now the way we have defined this, we can see 1 is accepted, 1 is not accepted, because if you put 1, so delta, because 1 is accepted 1, so delta hat of Q0 1, this is going where? So, we are at Q0, we go to here, we go come back to Q0. So, this is not accepted, 1 is not accepted. Now, 0 is accepted, 0 is not accepted, because delta of 0 is remains 0. Okay. So, now, two symbol like 1 is accepted, 0 is not accepted, 0 is not accepted, because it will be remain at this, 1 is not accepted, then 0 1. 1. So, delta hat of Q0 1. So, this is basically Q0. If we first we see a 0, it will be here, then we see a 1. So, it is accepted. So, 1 is accepted. 0, if we see a 1, we will reach there, and if we see a 0, this is Q1, because if we see a 1, we will go there, and then we see a 0, we will hop there. So, this is accepted 1 1 is not accepted. So, now we check 3 means 0 0 1, this is accepted. What is delta hat of Q0 0 0 1? So, Q0 we see a 0, will be here, we see another 0, will be here, and we see a 1, we will go there. So, this is accepted. So, 0 0 1 is accepted. Okay. Like this we can check, this is the same language. If we have a even number of 1s, because if we just have even number of 1s, we will just go there. If we have odd number of 1, we go there, we come back here, again we go there. To go there, we need to have another 1. So, this is the way we construct this. Is this clear? So, this is the same language as this. So, this is L of A. So, all the string which consist of even number of 1s, that will be accepted by this. Okay, like 1, like we can take 1 0 1 1. So, what is delta hat of Q0? This we will start with Q0, we will go here, then 0 will remain there, then 1 will come back here, then again 1 will go there. So, this is even number of 1. So, this is Q2 accepted. So, this is accepted. So, this is the set of all possible string, which is having which is having odd number of 1s. Odd means either 1 1, 3 1, 5 1 like this, which is having odd number of 1s, these are all accepted. So, this is a regular language. This language is regular, because we can construct a finite automata which is accepting the, this is a regular language, which is accepting the all the string from this set, then it is called a regular language. Okay. Then we can have another example, like so now the question is every language is regular? No, we will come later stage that there are certain language which are not regular. I mean, we cannot construct a finite automata which is like this language 0 to the power n, 1 to the power n. So, number of zeros is n and number of ones is n. So, there are equal number of zeros and equal number of ones, zeros followed by 1. So, for this language we cannot construct a finite automata DFA, or we will see NFA is also not possible, because the DFA has no memory. We cannot count that how many ones we have encountered. There is no extra, there is no memory to count that. So, how to count that? We have encountered, say, if we have 0 0 1 1. So, we have 2 zeros, then followed by 2 1s. So, how to count, how to store that number of zeros? So, this is not possible in this structure. So, this is possible in, it is called push down automata. So, we will talk in more details on that later stage. So, it is not, so this language is not regular, because there is no finite automata which can accept this. So, we will discuss more on this type of language. Let us take another example of regular language. So, suppose again sigma is binary string. Okay. Now, suppose we define a language like this, set of all string binary strings ending with 0 0, ending with 0 0. Last two bits 0 0. Okay, so this we can write in this way. This is W 0 0. W belongs to or x 0 0. X is coming from x 0 0. X is coming from sigma star. It could be epsilon also. Okay. Now, the question is this regular? Is L is regular? Is L regular? Okay. So, this is the so to be regular, what we need to have? We need to have a DFA, finite deterministic finite automata which can accept this. So, can you try that? Yeah. So, can you try to have a DFA with this? So, let us just try to construct a DFA, like suppose we have Q 0, Q 1, two state is not enough, because we have to see 0 0. I mean, we will see, I mean, whether it is possible or not. So, this is the starting state. Now, if we see a 0, we can go to another state with the hope that from again if we see a 0, we will go to the final state. So, this is the intuitive idea to construct a DFA like this. Now, after reading 0, if we see a 1, so this is here. So, we if we see a 1, we will hop here. So, and if we see a 1, we have to come back here with the hope that we will again see the 0 0 like this. Okay. And from here, that is okay. And from here, once we reach there, then if we see a 0 here, we can be here, because that is also. But if we see a 1, then we have to come back here. Then we have to come back here, because if we see a 1, then we need to have another 2 zeros for accept this. So, this is the construction. This is the finite state machine. So, what is delta? So, what is our A? A is Q sigma delta Q 0 F. So, what is Q? Q is consists of 3 states like Q 0, Q 1, Q 2, and F is nothing but Q 2 final state, and sigma is 0 1. What is delta? Delta is like this. So, we have 2 inputs 0 and 1, and we have Q 0, Q 1, Q 2. So, from Q 0, if you see a 0, we will go to Q 1, and if you see a 1, we will remain at Q 0. From Q 1, if we see a 0, we are going sorry, this is, yeah. So, this is Q1s, right. So, from Q1 if you are seeing a 0 we are going to Q2 final state, but if we see a 1 we are again coming back to Q0, and then from Q2 if we see a 0 we are going to Q2 again, but if you see a 1 here we have to come back to Q0, start again that thing. Okay. So, this is accepting the string like this 0 0 because 0 0 is going there, then the 0 1 is not accepting, then say 0 1 0 0. So, all the string which is ending with 0 0 it is accepting. So, L of A is nothing but this L. So, this is a this L is a regular language, because we do have a DFA which is accepting this language, which is accepting the all string of this language. So, if we can construct such a for a given language, if we can have a finite automata which is accepting all the string of that language of that set, then we call it is a regular language. So, hence this is a regular language, because we can really construct a DFA which is accepting this. Thank you very much.